Good morning and welcome to another MEscope webinar. My name is Mark Richardson, Marketing Manager with Vibrant Technology, and I'm joined by my father, Mark Sr., CEO and President of Vibrant Technology. And we're bringing you another webinar. We haven't had one of these in a few months now, so it's good to be back, and we welcome all of you. Today's topic is extracting 3D mode shapes from cell phone video. We are going to go through a few PowerPoints to start with, then we will actually get into the MEscope product and walk through that a little bit. We'll finish with some pricing, and then we will actually have time, hopefully we'll have some time for some questions. So I encourage you, if you have questions during the presentation, to go ahead and type your questions into the questions dialog box there on the right-hand side of your screen under the go-to menu. And we'll get those questions answered at the tail end of today's presentations. Incidentally, everybody will be on mute for the duration of the presentation, and it is being recorded, so we'll get a recording out to you probably early part of next week. We'll upload that to the Vibrant Technology YouTube site, and I encourage you to take a look at that site if you want to go back and review any of the past webinars, or if you want to go back and review this one. There's lots of great content out there, webinars, training content, tips and tricks, you name it. It's all out there on the YouTube side. With that, let me hand things over to Mark Sr. and we will get going. Dad, take it away.
Yeah, thank you, Mark. Welcome to all of you. It's a nice, sunny, bright morning here in Southern California. So we're spread around, and with the benefit of streaming videos and so forth, we can share a lot of features in MEscope, and that's what I intend to do here today. MEscope was designed to implement the idea that a picture is worth 1,000 words. So when we collect a lot of data on a machine, or if we do a modal test and collect a lot of accelerometer data, and now we're using cell phones and even high-speed cameras to collect video data and extract vibration from that, there's just a whole new world of opportunities for anyone of you, and I'm sure all of you are involved in one way or another in vibration analysis or machinery maintenance, or you're just a modal testing expert that your company calls on when they have a resonance problem. And virtually everything vibrates. So we'll talk a little more about that. But I'm here at the Vibrant website right now, and I'm going to go up here and to the resources page. And any of you, whether you own MEscope or not, can go to this page and look at our technical papers. So we're constantly writing new papers, and this webinar is going to explain a tech paper that I just finished, that we finished here at Vibrant, and we're going to present at an engineering conference called the International Modal Analysis Conference. So that started back in the early 80s, 1980s. It's been going for all these years, 40 years of practitioners who do modal testing, or even FEA, or if they're a civil engineer, maybe they're using strain gauges on a bridge, different ways to identify and characterize resonance vibration. So this, you can see there's some different categories here. This is a more recent one where we're writing papers, and IMAC is my favorite one. I've been attending there for the last 40 years. Operating deflection shapes, signal processing. There's just a lot of technical information for those of you who like to read. And that's not common among engineers, so making a joke about that. But and then down here at the bottom, if I say, well, let's go to tech paper number 83, I can scroll all the way down here to the bottom, and there is tech paper number 83, extracting 3D mode shapes from cell phone videos. So I'm going to click on that. And here is the paper. So all this information is out in the cloud. It's you can go on our website at any time, and this is free. Now, our application notes require that you own an MEscope license, and those are they're directed more at actually using MEscope, going through step 1, step 2, step 3. But we're going to do a little bit of that today. So I want to download the iMac PowerPoint presentation. You can see that this is scheduled for February 2025, so we're kind of getting ahead of ourselves here, but this is downloading the PowerPoint presentation, and I'm going to open the file, and we'll start going through some of that. Okay, so here it is. And this is the presentation that we're going to present in February in Orlando, Florida at that technical conference. And we used to go to a lot more of them, but because of COVID and economics and so forth, there are conferences in Europe, there are conferences in the Middle East. We're kind of small at Vibrant. We don't travel to those, although in the past I've attended some of them. But this is the one we've continued to attend each year, and we've got another technical paper that we'll present that has to do with machinery health monitoring next month. So stay tuned. So here's what we call a video ODS animation. So we've kind of trademarked this idea. Everybody, and we certainly have competitors that have software and systems and much more expensive than MEscope. MEscope is just software. So if you got a cell phone in your pocket, you can record a few seconds of a video and bring it into MEscope and recognize a problem like this. Here's what's called soft foot. So immediately the picture is worth 1,000 words. And so an ODS, we'll use this term a lot. We'll use the term mode shape a lot. An ODS is an operating deflection shape. So this machine is operating, and what I've recorded in the video is the ODS. And you can see it's relatively dark. One of the advantages of your cell phone is that it doesn't need floodlights. Now, when you go to a higher speed camera, we'll talk more about this, typically you got to put floodlights. Kind of like going to the photo studio where you get a family picture done and they put floodlights on and brighten up all your faces so that the photo comes out well. But the cell phone technology that's available today, and some of the cell phones will actually sample it up to 1 kilohertz now. So that covers a lot of mechanical structures. My cell phone, an iPhone, and this video was taken at 60 hertz, and that's or frames per second. So that's very common among all the cell phones. And but the Google and the Apple phones can sample at up to 240 hertz. So if you multiply that by 60 RPM per hertz, that takes you up to over 7,000 RPM. So you can analyze a lot of data and look at a lot of vibration problems, certainly in larger machinery where the frequencies are lower. Okay, so here's some rules of modal analysis. Any object with mass and elasticity will vibrate. However, forces must be applied to cause it to vibrate, and many times we don't know where the forces are coming from. When the Earth vibrates out here in Southern California, the forces that create the earthquake are due to the different plates on the surface of the Earth that are rubbing against each other, and then they let go, and that causes an impulsive force. And I have actually witnessed, having lived in California for many years, a mode shape of the surface of the Earth. It's just as plain as looking at the mode shape of a flat plate. So resonant vibration is defined by modes of vibration. So when people say, gee, I think I have a resonance, or even an acoustics problem, because most things behave like a speaker, they push the air around when they vibrate. So you might even hear the vibration, but it's due to resonances. All modes are excited at all frequencies. That is one of the assumptions we make when we curve fit data, broadband data, and extract modal parameters. And the typical parameters are frequency, damping, mode shape. Another term for mode shapes they're called eigenvectors and eigenvalues. The term eigenvalue means a unique value, which is the frequency of the resonance, and the eigenvector is the mode shape. So those are more mathematical, and they're German terms that better describe a resonance, its frequency and its shape. And then the final one, all vibration is a summation of mode shape. So we'll come back to this, and we're going to do some curve fitting on some video data. And so here is a whole bunch of terminology. One of the problems we engineers have with us, if lawyers have their own legal speak, we engineers have our own language that we use, and then 3-letter acronyms for virtually everything. So the government, it's got hundreds of agencies, and they all have 3-letter acronyms, and so we got our own. What gets extracted from a video are what we call time waveforms, so TWFs. I'm going to use that term a lot. And we will get thousands of them. An example I'll show you here in a minute. We get about 1,000 TWFs off of a 15, well, multiply 15 times 60. That's how many samples we get from a 60 Hertz frame per second video. So we don't talk about Hertz or sampling frequency as much, but it's exactly the same thing. We talk about frames per second. So when your cell phone records a video, it's exactly the same as an FFT analyzer or data acquisition system recording voltage off of an accelerometer or an impact hammer. Digital Fourier spectrum, this is the result of applying the FFT to time waveforms. So we'll see that in a minute. Time waveforms and DFTs are displayed as soon as we come out of the processing, and in MEscope we call it a wizard for processing the raw video. Now, the FFT has a law that says the maximum frequency I can extract or display in the spectrum is 1/2 of the sampling rate. That's just a law of nature. Can't violate that. And again, the fast Fourier transform, the FFT, converts time waveforms to DFTs, and then the inverse of that converts the DFTs back to the time waveform. So that's called a one-to-one and onto transformation. All the vibration information is contained in the TWFs that we extract from the video. That's our assumption. And the DFT has the same information in it, only in a different form. It's a spectrum. We talk about auto spectrum. We call that a auto power spectrum, or APS. That's a DFT conjugated multiplied by itself. So again, we're working with complex numbers, real and imaginary, magnitude and phase, just typical engineering data. All vibration is represented by complex numbers or complex data. A cross power spectrum is a little different than an auto, where I take two different signals, and we use the term roving and reference a lot. A reference is a fixed response position. Roving is moving around. So in the case of a video, the pixels in each frame of the video are the roving responses, and then if we're going to calculate anything from those roving responses, we need to pick one of them as a reference. And that's what we do with when we do ODS-FRFs. Now, there are other terms used for ODS-FRF. This is a term that we've created at Vibrant, and we use it a lot. It's like an FRF, but it's different. FRF always requires that you measure the force that causes the response. So if I do an impact test, I measure the impact force, I measure the accelerator response, or with a video, the response due to the impact, then I can calculate an FRF, a frequency response function. But if I can't measure the force, in the case of a running machine, then I can still calculate something called an ODS-FRF. And that is a combination of the auto power spectrum of a roving response and the phase of a cross spectrum of the roving relative to a reference response. And remember, the reference is fixed. So that'd be like a shaker test where the shaker is fixed and I rove an accelerometer around. Again, the frequency range, or we have various terms that we call it the frequency span of the frequency domain measurements. They're all the same, the DFT, APS, XPS, ODS-FRF, they're all the same. Okay, so steps to extract 3D mode shapes from a video. These are the 5 steps we're going to go through here in this presentation. Now, this is a recording of the animation in MEscope of what we call a video ODS. So on the left is a 1 frame. Now, when it switches up to the top, you can see the little finger here in this video going to the top. This is a sweep animation through the time waveforms that were extracted from the video. And each sample of the time waveforms corresponds to a frame of the video. So when we do a sweep animation, we can actually show, we can change the picture with each sample of time data. Okay, now we're back sweeping through the time data, and the animation, the picture is changing. You can actually see the wheel moving here. It's got a little bit of a reflective tape on it. So when we're animating out of the time records, we can actually see every frame. And then of course we can change amplitude and speed of the animation. So when the arrow jumps down here to the bottom in the video, we're actually animating at one of the frequencies in this spectrum. And we have a peak cursor on here. You can see a little red dot. It's animating the ODS at all the peaks in the DFTs that were computed from the time waveforms. And typical are thousands of time waveforms and thousands of DFTs. Remember, they match each other 1 for 1. And then the animation in MEscope, and we can crank the amplitude, and what you're seeing is this is, that the wheel with a pulley on it is moving around the most, and a lot of the points aren't moving much at all. But when I say points, typically every frame of a cell phone video is about 1,000 times 1,000 pixels. So that's 1,000,000 pixels per frame. And that's just way too much data. What we do in MEscope is we take that data. Okay, well, we're going to show this machine here a little bit, and we've used this for a number of different experiments where we put screws on the inner and outer rotors. You can screw them in there and create unbalance. So that's what we're looking at here. We're seeing some unbalance, and you can actually see from the video one of the screws that's on there. Doesn't matter which one, they're all different, but we're creating some unbalance. And then you can see the whole machine is just rocking on its rubber mounts, sitting on a table. So that's going to be, we're going to try to model that with 3D FEA data as we go forward here. So here is a picture kind of describing what we just looked at in animation. We got an animated ODS and magnitude and phase of selected points. Well, where do those points come from? Well, in MEscope, what we do is we create a rectangular grid of points. And when you're processing the video, you can decide how many points you want in the grid. I mean, you could start out with a 10 by 10 or 100 points. This one is a lot more points. You can see the grid has 1,688 visible points. Now, the other thing we do when we process is we remove all the points that don't have very much motion in them, like the background. We don't care about points in the background. We only care about points on the machine itself or the test article, whatever it is that you're making a video of. So you can remove all the other pixels and points from your point grid because you're only interested in the motion of the points on the machine itself. Now the advantage is I can put the actual magnitude and phase, and you can see there's magnitude in inches per second. So again, this is something we can do with frequency domain. We can integrate and differentiate very easily the data. Whereas in the time domain, it's more difficult. There's probably 100 algorithms to do integration differentiation. But in the frequency domain, we have the advantage of just algebra, multiply or divide the data. So a video records displacement from frame to frame to frame. That's what the algorithm does that we have in MEscope. But here the data has been converted to velocity by simply differentiating in the frequency domain, multiplying by frequency. So many machinery people use velocity as kind of a rule of thumb. Anything that's vibrating over an inch per second is about ready to go through the roof of the building. Anything less than a half of an inch per second is behaving properly. I mean, everything is going to vibrate. You can see these vibration levels are all very low. They all got 0.0 something on them. So that's an advantage of using a point grid in MEscope and then removing any points, just making them invisible basically, so that we don't have the time waveforms or the DFTs. But you can see we still end up with a lot of data here from a video, a lot more than you would ever get from using accelerometers. You would never have 3,376 accels. But that's what this point grid is telling you, that we've got X and Y motion, vertical and horizontal, 2D motion of this test article for 1,688 points. And then likewise, we got the same number of DFTs. And the DFTs, of course, are going to show us where the resonances are, because those are going to be peaks in the data. So here's another animation. And in MEscope, we talk about an ODS. So when we're animating up here, it's the same animation we were looking at before. Crank up the amplitude, you can see that the machine is just rocking on the tabletop due to the unbalance on this outer rotor here. Now we could have had unbalanced screws on the inner, but I don't see any evidence here. I certainly see some evidence of a rotor on the outside. So when we sweep through the time records, we call that time-based ODS. When we do a sinusoidal animation, we modulate with a sine wave the ODS data. And again, we got 3,300 measurements down here animating all the points that are still visible in the X and Y direction. So this is where we get to analyze our results. Now, let's talk about ODS-FRFs calculated from the time waveforms. Again, we showed in an earlier slide the magnitude of the ODS-FRF is the auto power spectrum of the response DOF at a grid point. So every grid point, we got vertical, horizontal motion. the phase of the ODS-FRFs is the phase of the cross power spectrum between the response DOF and a reference. Now, when we extract data from the video, a lot of the points don't move very much, so they're not of as much interest. So what we do in MEscope when we come out of the, let me just get the animation going here again. When we come out of the, what we call the wizard, processing the raw video, we order all the time waveforms and their corresponding DFTs by magnitude. Now, that's just a simple way of giving us the records of the most motion. Now, in this case, this wheel with the pulley on it has got the most motion. So these TWFs up here are going to be for that wheel and the other two wheels because they're moving around the most. But if I go down here to the DFT and crank up the amplitude, now, yeah, the amplitude of these wheels goes crazy, but I can clearly see the motion of the base plate now. So that's, again, the video ODS animation allows us to do things like that. Okay, so here is an ODS-FRF, and you can see the maximum frequency of this data is 1800 RPM, and that is 1/2 of the sample frequency of the, or the frames per second of the video, which is 3600 RPM. Divide that by 60, and that's where we get the 60 frames per second, or the 60 hertz sample rate. So relatively low sample rate on this machine, but we see three clear peaks here in the data. One of them is what we call the first order, and that is the running speed of the machine. So we adjusted the machine to run at about 1000 RPM, and that is the rotor here. There's a belt, and then there's a motor behind this power source here. But here I can turn this little wheel and basically set the RPM of the machine of the rotors and this pulley here to about 1000 RPM. So that's what the peak cursor is showing us here too. But let's go back and see what else is in this data. There's a couple aliased orders in this data. So aliasing is a problem with a video that we don't have with accelerometers and an FFT analyzer, because that hardware will have an anti-aliasing filter that'll filter the analog signal before it's processed in the analyzer to remove the higher frequencies. We don't have that luxury with a video. There's no filtering. So what we see when we see peaks in the spectrum from a video are actually aliased orders. So you can see I got one here at 1500, and I got another one down here at 564. Well, those numbers, we can calculate exactly what they should be. The first order is at about 1000 RPM. That's the running speed of the machine. That shows up bigger than life right here at 1000 RPM. The second order should be at 2000 RPM. Well, that's beyond 1800. So that one got aliased with this simple math. You just take the second order minus 1800, and that shows up at 1572, which is exactly where it shows up. The third order, 1800, 3000 minus 1800, and then subtract that from 1800 because the aliasing causes the peaks to wrap around 1800, and that shows up at 558. The calculation says 558. Well, it's actually at 564. Pretty close. That's within one delta F. If we go through more of the math, we can look at that. So we're going to curve fit this data, and I'll take you through the slides, and then maybe if there's questions, we can go back and actually curve fit the ODS-FRF data. But there's a couple things that go on here. You can see the red curve fit function. We use the quick fit, and it's going to not only measure the frequency of the resonance peak, so we know that 1,000 is correct, these other two frequencies are aliased, but it's going to measure damping in RPM. Here's damping in percent, and then what we call the residue, which is the strength of the resonance in each measurement. And remember, we got like 3,300 measurements here, so quick fit goes through very quickly. And then when we save the mode shapes, and we call this an OMA mode shape. So anything that's extracted, any mode shape that is extracted from a video where we can't measure the forces. Forces are distributed all over this machine. There's just no way to measure them. And even if we put accelerometers on a machine like this, we couldn't really instrument the rotors and the pulley. So videos give us information beyond what we can do with a traditional modal test. However, it's all the same. We call them OMA mode shapes or operating mode shapes. OMA stands for Operating Modal Analysis. And we can differentiate the mode shapes. Again, these are frequency domain functions. They have frequency and they have a shape. So in MEscope, we can convert, we can just differentiate the displacement data to velocity. So we're looking at velocities here. And again, for machinery maintenance people, that's useful data because they want to know, you know, somebody's complaining the machine is shaking the building. Well, they can actually take a video with their cell phone and see how much motion is actually there. Now, another thing that goes on here, we can't use an FRF-based curve fitter on ODS-FRF data directly. So in MEscope, when we do this kind of curve fitting, and you can see the curve fitting function land right on the data, this is the magnitude of one of the measurements actually is an envelope. This is something else we do in MEscope because a lot of your measurements don't have much motion in them. They're, you know, points on the video frame that aren't moving compared to, in this case, the pulley or the rotors. So we compute an envelope so you can actually see where the peaks are. Any individual, and again, there's 3,300 of them here. You can see this one is labeled at 6757 measurement. So there's just a lot of measurements here in this data. And we call them OMA FRFs because we've curve fit them now. And in order to do that with an FRF curve fitter, we apply what's called a deconvolution window to the raw data. Then we can curve fit it with an FRF base curve fitter. All right, so how do we get from 2D to 3D? These mode shapes are just 2D. They're just the structure moving in the horizontal and vertical in the frame of the video. So that's all we get with the video. That's another limitation. Not only do we have aliasing in the data, but we're limited to 2 dimensions. And of course, we can take videos from different directions, and we don't have a way to paste all that data together. Actually, you can do it in MEscope, cutting and pasting motion from, let's say, 2 different directions, and then get 3D mode shapes that way. But that would be a lot of work. I'm going to show you a simpler way to do it, and that is to use SDM, which is one of the tools we have in MEscope. And it's called eigenvalue modification. This, again, a mathematical term. Remember, mode shapes are eigenvalues or eigenshapes or eigenvectors. So the 2 terms we use to mathematically describe mode shapes are either eigenvalue, which is the frequency, or eigenvector, which is the mode shape. So SDM is a modeling algorithm. It's also called eigenvalue modification because what it's going to do is when we add FEA elements to a 3D model, which is this block over here, and then we give SDM the mode shapes of the unmodified structure, it computes the new mode shapes of the modified structure. So pretty simple. It's similar to FEA, but it works with mode shapes as opposed to the physical properties of the structure itself. Now we're going to use those physical properties to get started. And this is just some more about SDM and the types of elements that you can use in MEscope. But what I did, and we also have an FEA option in MEscope. Now it's not a replacement for Nastran or ANSYS or any of the bigger packages. And those of you who do experimental work, you probably have another whole organization in your company that builds FEA models. It's now called digital twin. That's a new term for building an FEA model of some mechanical thing that you're building, a car body or an airplane wing or whatever it is. In MEscope, you can actually build simple FEA models. So I did that. I built an FEA model of one of the bearing blocks, solved for its modes of vibration in free space, what are called free modes. Then I just duplicated all that and for the other bearing block. And then I attached, and then I built an FEA model of the base plate. Again, very simple, the easiest. I'm no FEA expert, but I can do that much. Then I just geometrically added in MEscope the two bearing blocks to the base plate, and I connected them together with very stiff 3D spring elements. This is SDM now doing this. And you can see I don't even need the points to match up between the bearing block and the base plate, which is an advantage of SDM because it only works with mode shapes and elements like these springs. So I put very stiff springs in 3 dimensions at each of the point, or actually they're just in, you can see they're in 3 different dimensions here. And that's very easy to do in MEscope. And so here are the mode shapes. Oh, and then the second step was to attach the base plate to a rigid base, and the rigid base being the tabletop. And here are the mode shapes that SDM produced. So you can see rigid body motion. Now we've got what's called a flexible body mode shape, just a bending mode of the base plate. And then, because the geometry is not symmetric in this case, the mode shapes come out asymmetric in the sense of the way the base plate bends. So these are the FEA mode shapes that we're going to curve fit to the 2-dimensional data, the OMA data, the mode shapes that we extracted by curve fitting the ODS-FRFs. So let's move ahead and just look at those results and talk about that. Now, in order to do this curve fitting, this second curve fitting step, curve fitting the 3D mode shapes to the 2D mode shapes, we need to match up some of the points on the video model with points on the FEA model. So that's what we're looking at here, the video model on the left, the FEA model on the right. And again, we got a fancier geometric model, and we're using interpolation to make it look more realistic, but really the FEA model we're using are just the bearing blocks and the base plate. So I'm using up too much time. I'm going to go a little quicker here so we can get to questions and maybe review some of this. This is what we call mode shape expansion in MEscope, and this is a property or a capability of our Modal Pro package. And we'll get into what we mean by a Modal Pro package in a minute, but I can take shapes with many impounds. Those are degrees of freedom or measurements in MEscope. Every element of a shape table or every measurement in a data block we call an impound, a measurement number, if you will. Another acronym that we use in MEscope. So we're going to take the 2D mode shapes with a few degrees of freedom, just 2D, X and Y motion at these 5 points. So 1 on the top of each bearing block and 3 down here on the base plate. And then we're going to number those points the same on the FEA model. And of course, the FEA model has 3D motion. This, excuse me, only has 2D motion. So that's what we're doing here. And the mode shapes are the only thing that's needed, not the frequency, not the damping, just the mode shapes to curve fit the 3D mode shapes to the 2D. Now you might say, well, that's an awfully crude FEA model. Yes, it is, but we'll get some reasonable looking results even with a crude FEA model. Now you can go down the hall at your organization and get some FEA expert to design a fancier FEA model and solve for its mode shapes and import them into MEscope and do the same thing. But we're just trying to get a look here at how the 3D motion of the machine behaves using fairly simple mode shapes. And again, frequency and damping don't matter. It's just the mode shapes themselves. And those are, in a sense, a reasonable deformation of the bearing blocks and the base plate of this machine sitting on a fixed foundation. So those are assumptions that you would make in any FEA model, unless you wanted to go ahead and model the whole tabletop and so forth. Here's a little bit of mathematics for your mathematicians. This is showing what we call mode shape participation. So I've got a matrix of mode shapes here called U, a matrix over here of mode shapes called V, and a matrix of numbers in between, which we call participation of U in V. So these are complex mode shapes, magnitude and phase. Again, normal modes are just real and imaginary, so they're not complex. A normal mode that we get out of an FEA. But in the real world where we have damping, the OMA mode shapes have damping. We saw that when we curve fit the data. And then we get a participation matrix. So a little more math here, and this is how we solve in MEscope for the participation matrix. This is a least squared error calculation where we go through transpose, conjugates, inverse, and we come up with a set of participations of the FEA mode shapes in the two-dimensional OMA mode shapes. So here's a little more math showing how that works in MEscope, and this is all in a shape table, a couple of commands that we call mode shape expansion. The 3D mode shapes are curve fit in a least squared error, and the FRF curve fitting is all least squared error curve fitting also, so no difference there. And again, we use the frequency and damping that we got from the video to label the frequency and damping of the each expanded mode shape. So here's the result. Here are the 3D mode shapes of the first 3 orders that we got from curve fitting the ODS-FRFs. Those are called OMA mode shapes. And the frequencies of the first and the third are aliased around 1800 RPM. So we would need to correct those, which is easy to do in MEscope. They would be 1,000, 2,000, 3,000, as opposed to the alias frequencies. But everything else is accurate. And you can see the damping. Now there's one other step that was taken when we saved the curve fit 2 degree of freedom mode shapes. We remove the effect of the deconvolution window, which adds artificial damping to the modes. So that's another part of curve fitting ODS-FRF data that's built into MEscope. But you can see magnitude and phase of the 5 points and a mode shape, each of those mode shapes that looks very realistic in the sense that the machine is just rocking back and forth on its rubber mounts due to the unbalance here on this outer rotor. And there's a little bit of flex of the machine also. So here is another graphic that shows us how each of the FEA mode shapes participates. So this is the participation matrix in a graphical form. And we can see that the first 3 mode shapes dominate the participation, although all 10 mode shapes of the FEA 3D mode shapes do participate in the 2D OMA mode shapes. The first 3 dominate. Well, what did they look like? Those were what I would call rigid body motion. Let's just go back and look at them. Okay. Okay, so here they are. So there's the first mode, 0 frequency is just, there's the second mode, there's no resonant frequency there, it's just moving on its spring. There's the third mode. Now it's got a little bit of frequency, 8 hertz, but it's basically just moving on the springs. Now we're getting deformation of the base plate, the bearing blocks. This one is almost, again, rigid body motion, but you can see there's just a lot of deformation at the higher frequencies of the FEA mode shape. So if we go back and look at the participation, the first 3 modes dominate the curve fitting process, going from 2D to 3D. And then this is the, let's go back here. Here is just a picture of the rigid body mode shape. The first one is moving in this direction. The second one is moving in that direction. The third one is the twisting on the springs. And then the fourth one is a flexible, actually mode number 9 is the base plate is starting to bend a little bit. So mode number 9 is this one here. You can see it's popping up in all 3 of the OMA mode shapes. It's curve fitting a little bit, but not as much as the first 3 mode shapes. So anyway, let's wrap up. Cell phone, everybody's got one in their pocket. It's a low cost, non-contacting. You can see things from a video that you're not going to see anywhere else by putting Excels or using a laser vibrometer or whatever. Here are the different settings in my cell phone: 30 FPS, 60, 120, 240, and those will allow us to analyze data in the RPM range up to 7,200. ODS-FRFs are calculated directly. The advantage of the ODS-FRFs over the DFTs, now I could have curve fit the DFTs also, but the ODS-FRFs I can do spectrum averaging, and that cleans up the measurements quite a bit, so that when we curve fit them, we get some pretty good OMA mode shapes. So then I built 2 models, very simple, one for the bearing blocks, one for the base plate, and put them together with springs, attach the bearing blocks to the base plate, and then the base plate to a fixed tabletop. The stiffnesses of the springs to the tabletop, not that important. I could make a guess at what they might be, but the mode shapes are the important part. And then we did a second curve fitting step to get the 3D OMA mode shapes and the participation of the mode shapes in the, here's a little typo right here, that should say 2D. Oh no, this is the participation of the FEA mode shapes after we've done the expansion to the 3D OMA mode shapes. So this is the 3D OMA mode shape that we calculated. There's 3 of them. And they're all very similar in mode shape, but different in value. And of course, the running speed, the first order is the one that dominates the response of the machine. Okay, let me just wrap this up with a quick look at our price list to discuss numbers with you. And then we'll go to the Q&A. Hopefully, Mark, we got some.
Yeah, if you have any questions, go ahead and type those questions in. Right now, we got no questions, so either you put everybody to sleep or you did a good job.
I put them all to sleep. Sorry about that. Let me just go to the price list here very quickly and give you some numbers to contemplate if you're interested in purchasing MEscope or options to MEscope. Now, once you own an MEscope license, I like to say MEscope's like a food chain. Many of you may own the 620, the VT620, which is just visual ODS. Typically, import time-based, frequency-based data from an analyzer, and you can curve fit it, of course, but not with this package. You can just animate the ODSs from the raw data, which is what I started off to show you. Now, then we do up the food chain, we go up here to modal. Now the curve fitting I did, especially the second curve fitting, when I curve fit the FEA mode shapes to the OMA mode shapes, that requires a Modal Pro package. So you can see the price here for 12-month license, or what we call a perpetual license. So you own it forever and ever. And then here's SDM, which I also used to take the simple FEA mode shapes for the base plate and bearing block and merge them together, and then also model the machine sitting on a fixed base. So, you know, down here, you can get the video processing and the FEA analysis, you get it all if you order this package down here. A little more expensive, but still, compared to the competitors, it's a bargain. So this describes our options. And you can see up here, each of these packages starts off with a 620, the visual ODS, and then here we add signal processing, and then we add curve fitting, add more curve fitting, SDM with the advanced curve fitting, and then down here is STN stands for soup to nuts, everything that you can purchase. So let's just go down here and look at, let's say you already own SDM and you just want to process your videos, then this is the option you want to purchase, the VES 9000. $7,000, and again, compared to the competitors, this is a bargain that will allow you to not only process your cell phone videos, and as I said, some of the cell phones now may cost you a little bit more, but they will sample up to 1 kilohertz, whereas an iPhone only to 240 hertz right now. But that technology just keeps getting better and better. And it doesn't require floodlights, which is, you know, it's just a lot more work to set all that up. This is another package we have, the 430 package called Enhanced Video Animation. You get a license for this. Now you can just purchase this as a standalone, or if you purchase this option to your VES package, you get a license for this also. Now what this is a touchscreen interface, different graphics that you could use out in the factory or the field with your cell phone and a touchscreen computer. So that's about it. A lot of other things to talk about here, but I just wanted to show you some of these prices. Now, if you don't own MEscope, here's the basic package, the 440 package, still quite reasonable, and that gives you the ODS, the visual ODS, so you can do all the animations, plus the video processing. So that allows you to do what I first showed you, the animation of time or frequency from your video data. This is the second level where you now have signal processing, where you can compute ODS-FRFs and so forth, a little more accurate description of your data, but then you probably want to go to modal to do the curve fitting I showed you today. All right, well, that will wrap it up, Mark. Do we have any questions?
We just received a question on like more of a comment, I guess. I was wondering if you ever tried performing modal analysis on a PCB using an ED shaker, shock machine, or halt machine, sometimes due to the nature of the test setup. The device under test is difficult to install accelerometers. This camera-based method seems like it could be a very neat solution. Well, absolutely, it does.
Absolutely.
That's exactly where this solution would be a good application for you when you have a difficult situation where you can't install accelerometers. That's where the camera really shines.
Yeah, I mean, there's just no way. Now, this one you could put accels around on this base plate here of this fan or whatever it is, motor pump, and you could discover that. But you couldn't even put accels down in here and get a clear picture like this. Remember, there's a grid of points behind this, so I can actually get off of the video. I can scale the video so that I get scaled data, just like with the accelerometer. And we've got a video on our website where we compare accelerometer data to video data, and with proper scaling of the video and scaling of the accelerometers, the results match up to a couple decimal points, which for engineering work is plenty. Now, people will say, well, it's just not very accurate. Yes, it is. It can be very accurate. But, you know, this animation here, you can't even get an animation like this. Now, granted, it's 2D as opposed to accelerometer data, which would be 3D, but you won't be able to see. And if you look at this carefully, you're actually seeing the mode shapes of the rotors built into this. You know, all vibration is a summation of mode shapes. So you can't see it as much in the time waveform, but if I go to the frequency waveform, you can actually see the mode shapes of these rotors, and there's no way you could instrument it. Yeah, with a laser system, but now you're talking hundreds of thousands of dollars. Here you can actually see the modes of the rotors. This one's very clear. This is a mode shape of the, you know, it's dominating mainly the unbalance of this pulley here, but you're getting information you couldn't get any other way. Anything else, Mark?
Let's see, the same gentleman, Robson, says, I've tried using high-speed cameras from another vendor before, but we were unable to capture the mode shapes for frequencies above 5 kilohertz, which is critical for my application.
Yeah, now you get up to 5 kilohertz, you've got to use floodlighting because the sensors, the optical sensors in the camera just don't pick up enough light. So that is a disadvantage of going to 5 kilohertz sample rate with a high-speed camera. You got to set up the lights and make sure you don't have flicker in the video and so forth. So again, cell phones are much lower frequency. We're talking about bigger structures, but if you're looking for mode shapes or resonances at 5 kilohertz, accelerometers are probably better and easier to use. Even there, you're getting up to the bandwidth limitation of the accelerometers. So yeah, if you're pushing the limits, as I said, you can, for $1,000, you can buy a Samsung or a Sony cell phone, carry that in your pocket, set it up on a tripod, forget the floodlights and sample up to a kilohertz and probably still get very good results. Now, these cell phones have intensity algorithms built into them so that they give you a very bright video, even in a dark corner. And we got some examples on the website of videos that were taken in dark places in a factory or a building without having all the setup. So again, if you're using accelerometers and you want to go to 5 kilohertz, use your cell phone at least to see what there might be moving around on the machine that you can see at a lower frequency, and it'll give you an idea where to put the accels to measure up to 5 kilohertz. But yeah, you're getting up there in frequency now for any video. I don't care whether you have a $20,000 video camera, you're going to have to use floodlights, and you still might not get a very good video because it's just such a high sample rate of the pixels in the video camera itself.
All right, another question here. I already have MEscope VES with SDM. What additional package would I need to get the ability to process videos?
Yeah, well, that's what
you want to pull that price list back up? We can show.
Let's go back and get the price list here.
Yeah, you got everything you pretty much need. You're just going to need
you got everything. You just need the video processing option.
Yeah.
So here's the price list. So $7,000, and that'll give you actually 2 different programs. So this is what you want right here. Visual VES 9000, $7,000. And that'll give you a perpetual license. You already have a VES package that's beyond this. If you got, any one of these packages up here, as I said, it's a food chain. If you got Modal Pro or if you got SDM or SDM Pro, you've got all the curve fitting that I demonstrated. All you need is the video processing. And I didn't go through that today. Maybe we could do that in another webinar. We've done that previously in other webinars where we start out with the raw video and then you end up with a animation like I showed you here. And here's MEscope. I can just start the animation right here from MEscope, animate, and so here's the same thing. We're sweeping through the time records. If I click down here, I'm now animating from the DFTs, the frequency records. So as soon as you purchase the VES 9000, you're ready to go. And you can not only do the ODS animation, but then the curve fitting.
While you're on there, we got a question. How do I know which package I have? You can show them right here.
Oh, well, go up here to your help menu and you go to your license manager and it will tell you all the options that are on your license. So my license here's my license number that's in use. It's the only one on my computer. It's a network license. So I'm actually using the network license server in the cloud that we use for Vibrant employees. So you can order a network license server, and that's like a library system. You can have multiple users anywhere on the planet who can check out a license from the server, run MEscope on their computer, check it back in, somebody else can use the license. So that's a very handy option to licenses, and that's what I have here. So I can go over here to my license server and I can borrow, just like borrowing a book out of a library. And it says it's not borrowed, but here's where the vtis.vibetech.com, this is where the Vibrant license server is located. Down here it says there's actually 7 seats available, and I'm borrowing one of them right now. I'm using one. So there's 6 other seats available to other Vibrant employees that have a MEscope license that is connected to the license server that can use, they have to have this 15125, then they can go to our server in the cloud and borrow a license, just like a library book. That's how that works. But if I go back to the license information, this is showing all the options that I have available. This is pretty much everything. Finite element analysis, SDM, advanced modal, basic modal. Here's some other stuff in here. Database console. These are some other things that I'm going to use next month when we talk about logging MEscope or mode shapes, the 2D mode shapes. We're going to use the same test article, the same video, log that data into a database and use something called FACS, fault correlation tools. And that compares mode shapes, one mode shape to another, and it says this mode shape was a mode shape that was put in the database when the machine was unbalanced. And so we'll look at machinery health monitoring using mode shapes in an archival database. So that's what some of this other stuff is about. Anyway, hopefully that answered the question. Just go to your license manager and it will tell you what you own in terms of a license.
And if you got questions or you're interested in purchasing a package, you can reach out to us at sales@vivetech.com. Or if you have a local reseller that you've worked with, certainly you can reach out to your local reseller and they can provide you some additional information on pricing and so forth. But we're happy to help you with that. And yeah, I think we'll go ahead and wrap it up there. And we will get another, like I said, we'll get this recording out on the YouTube channel and look forward to another one coming up next week, next month. We'll get another webinar on the schedule, and stay tuned to your newsletters and inboxes, and we'll get that out.
Okay.
All righty, let's wrap it up. Have a good one, everybody. Have enjoyed your weekend, and we will talk to you all soon.
Thank you all for coming.